Hello, my name is Hunter.
Hi, my name is Pierre-Alain.
Hi, my name is Manfredo.
And this is our presentation on the electrical properties of our materials. So for question one, we've been asked to write down the electron configurations for each of our elements. There are really two ways to do this. You either do it the long way or the shorthand way. The long way is to find out what number your element is in the periodic table, find the correlating number of electrons, and then fill out the various shells in sort of this pattern that you can see up there. I won't describe it too much, it's easier to see than for me to explain. The shorthand way, which is what I'm going to use and describe a little bit more, is to find the last full row of electrons. So for iron, you're going to be 26, so the last full row is going to be argon, and then you're going to count the number of electrons, which is this 4s2 and 6 in this d orbital to get to iron. So for nickel, you're going to have the same sort of process. Argon's the last shell. You have this full s orbital, this full, that's 8 electrons in this d orbital, and then you get to nickel. For indium, you come down another row, so your last full row is now krypton. You have your full s orbital, full d orbital, and 1 electron in your p orbital. And then for phosphorus, your last full orbital is neon. And then you have your full s orbital and 3 in your p orbital.
All right, so for question 2, we are tasked with discussing the band gaps of our semiconductors. A band gap really is just like the electrical differences between like the valence band and the conduction band. Smaller band means that a semiconductor can better conduct, while a larger band will result in like more insulating properties. So for indium, we looked it up and we found that it has a band gap of about 0.9 electron volts. And for phosphorus, there's various types, so we just noted all of them. For white, 2.1, red, 1.8, and violet, 1.5 electron volts, which they average out to about 1.8 electron volts altogether. However, black is like a bit of an outlier, has a lower band gap of 0.34 electron volts, which is pretty good for like semiconductor applications. And for our semiconductor, indium phosphide, it was found to have an electron gap or band gap of 1.344 electron volts. So for question 3, we're tasked with finding elements that can be used for N-type and P-type doping in our semiconductors. For P-type doping is when you have extra hole in the compound, which would allow for more holes in the overall structure, as opposed to N-type, which has like extra electrons in the whole compound. For indium, we found that for P-type doping, it's best to find, you can use bismuth down here, number 83, and silicon, 14. And for N-type doping, you can use phosphorus, and number 15, and germanium, number 32. And repeating the same thing for our second semiconductor for phosphorus. P-type, we found that you can use copper, of all things, as P-type doper. And for N-type, you can use silicon as well for N-type doping.
All right, so for question 4, we've been asked to find the mobility, concentration, and conductivity of our elements. So for indium first, indium is going to be a metal. So when we talk about mobility, concentration, we're really going to be talking about electrons predominantly. That's because, as you can see here, metals in general, their valence electrons fill the conduction band, which are going to facilitate that charge carrying. So when they move around, you're not going to have to worry about holes that are created as electrons jump up from the valence band. So for the electron mobility, you can look that up to be 8.6 centimeters squared per volt seconds. The electron concentration, sort of as we described here, that's going to be 3 electrons per atom, and then we're going to find the concentration of atoms, say, in a centimeter cubed. So that's done. We have our 3 valence electrons, and then the number of atoms per centimeters cubed is going to be found with the density, Avogadro's number, and molar mass. So we can take those, we can plug in our numbers for the density, 7.31 grams per cubic centimeter, Avogadro's number, and the molar mass is going to be 114.8 grams per mole. That's going to give us a total concentration of 1.15 times 10 to the 23 electrons per cubic centimeter. So then for our conductance, we're really only going to be worried about the electrons moving around for metals. So we are able to use this formula, which finds the number of electrons or the density of those electrons, the charge of the electron, and then the mobility. So we can take our values from that previous slide, we can plug them in here, and we get a conductance of 158,240 coulombs per centimeter volt second, or that simplifies down to Siemens per centimeter. For black phosphorus, this is going to be a semiconductor now, or a non-metal now. So now we need to worry about these valence electrons jumping up to the conductance band from the valence band. That's going to leave holes now, which we're going to account for in our calculations. So once again, we have our mobility to be 1,000 centimeters squared per volt second, and a hole mobility of 600 centimeters squared per volt second. The intrinsic carrier concentration has been calculated in a few different research papers to be 10 to the 15th charges per centimeter cubed. So for our conductance equation, again, now we are going to use the formula that incorporates both holes and electrons. So we have our equation. Once again, we're just going to sub in all our information that we got from that previous slide. So we have 10 to the 15th centimeters to the negative 3 times 1,000 plus 600 centimeters squared per volt seconds times your charge of your electron, and you're going to get 0.256 Siemens per centimeter.
So for the last question, we asked to go over the different applications of our semiconductors. So we're gonna do it for indium phosphorus and for indium phosphide. So at first for indium was at first used for emitters and collectors for PNP alloy junction in transistors. So this is what we got here, and also it was used for transparent conductive for coating the electroluminescent panels. Like you can see here, we have indium in it to allow it to shine brighter. And also indium was sometimes used in cold soldering in microwave circuits. So this is what we have here. So phosphorus is commonly used in semiconductor manufacturing, particularly in the doping process of silicon, which is one of the core material in most electronic devices. Silicon is used in every other devices, computers, cell phones, and others, and we use phosphorus as a doping in silicon. So as we can read, phosphorus is used as a donor dopant in silicon to create N-type semiconductors. As a reminder, N-type semiconductors are when there are more electrons than holes in our component. So as we can see here, we used the phosphorus as a dopant. So it's also used in white LEDs, as we can see in the image. So the LED is coated with phosphor material. So the phosphor absorbs the blue light emitted by the LED and re-emits it as a white light. In silicon-based solar cells, phosphorus is used to create N-type layer of the cell. So indium phosphide is used in various domains such as high-speed electronics, optoelectronics, photovoltaics, and others. So in high-speed electronics, it is used for high-frequency transistors, which are used in devices like microwave, radar systems, satellite communication, and mobile communication systems. In optoelectronics, indium phosphide-based LEDs are used in optical data transmission, remote sensing, and night vision devices. And in photovoltaics, indium phosphide-based cells are used in space solar cells and high-efficiency terrestrial solar cells. So this was a presentation about the electrical properties of our semiconductors. It was Pierre-Alain Gbalou.
Hunter Sanford.
and Manfredo Marroquin.